Welcome everybody. Thanks to the foundation for accepting the speech. My name is Johan Peltenburg. I'm from the Delft University of Technology. And we have actually been working with the framework just presented by Bruno. I have to say I was quite impressed with the framework, and we will get to see again some of the points that he mentioned in the end. I want to talk about a thing that has been going on in the big data analytics, cluster computing frameworks, and this is an Apache top-level project called Arrow, and it kind of solves a problem we were looking at for a while to accelerate stuff in the big data analytics world with FPGAs. So there's an outline to the talk. So this problem that we had is called serialization. I will go into that a little bit more. We will talk about that first. Then we will look at the Apache Arrow project. It specifies a formatting of the data in memory. We built an FPGA acceleration framework on top of that, also on top of other technologies such as CAPI and Snap. And then we did an experiment to see what we can do with it and how fast it is. And then I will conclude the talk. So let's look at the big data analytics landscape. There are many frameworks lately that allow you to very easily work with a cluster computing framework, cluster computing system. So some well-known are of course Hadoop and Spark, but there are many others. Most of these you see here are Apache projects, and big data analytics people and programmers, they like to use these frameworks because they're written in very high-level languages. So that allows them to very quickly set up programs that run on a big cluster. They want to do transformations on collections of data. They can be in a database, but they can also be just in memory. They want to do maps, reductions, and also filtering operations. Now, many of these frameworks run are built on Java or Scala, for example, for Spark and Hadoop. Some parts are written in C and C++, but this actually means that a lot of these frameworks run on a virtual machine. In this case, a Java virtual machine, which, if I give examples about how things are going internally, I will use that as an example. But others, like Python and R, they run on different interpreters. So now in this landscape there are countless of libraries, extensions. There's a huge variety of tools and languages being used, and this can cause a couple of problems. So when I start, I'm a PhD student in Delft, and my supervisor asked me a simple question. He said, "I want to attach an FPGA to Spark. Go and do it." You know, and I thought, okay, that shouldn't be too hard. I've done accelerators before. It's probably gonna work. But it turned out that yeah, we could do it, and actually we did it a couple times, but the performance wasn't so great. And one of the main reasons for this was that if you use these kinds of languages, very high-level languages, you're losing something that we all know from languages such as C and C++. And basically that's that you're in total control of what the data looks like in memory. And that is lost if you run on a virtual machine that does all this memory management and layouting of your objects in memory for you. That's actually quite annoying. So this was the question. Well, in the end, this was the question. Let's attach an accelerator to a JVM. And so what did we see? So first of all, the data is in runtime objects managed by the VM. So you can ask two questions: where are these objects? Where are the data? Well, it turns out that the VMs, they manage this. They manage the objects in memory, and they allocate it in some place. It's somewhere, but at the same time, this memory is subject to garbage collection. So it might be that the virtual machine moves the data around in memory and you don't know where it is at some point. This is like, for a lot of programmers, this is nice because they don't have to think about freeing objects or freeing data anymore. But for an accelerator developer, yeah, you want to know where the data is because otherwise you can't really move it to the accelerator. So this is one problem. Now there's another problem. What does the data look like in memory? It's for Java, for example, the Java specification doesn't standardize what the data objects actually have to look like in memory. So it standardizes a lot of things, but not that. So many different VM implementations can do it in any way they want. Now we usually look at the OpenJDK because we can read the source code. And it's also like a baseline implementation for many other JDKs. For many other implementations, sorry, of the Java virtual machine. And usually what we see, there's a header that holds specific information about monitors and locks and threads. There's a pointer to the class of the object. There are many other bits. And finally, we get to the fields of the object, where actually the data is that we're interested in processing. And even the ordering of these fields is done in a specific way that might not always be suitable for processing on your accelerator. So usually, if you wanted to solve this, what you had to do is called to serialize the data. You go into the data structure, you figure out where all the fields are, and you write them to some sort of buffer that eventually you copy to your accelerator. So I can give an example about a collection of strings, for example, in the JVM. So what you have to do, you have some collection objects, so this can be like a vector or a dictionary or something high level. And usually there will be, internally, the data will be stored somehow. So in the case of a large collection of strings, there can be a string array object in there. So you have to traverse 2 references there. That doesn't take a lot of time. But then for every string, you have to traverse more references, or, well, C people know them as pointers. In the Java world, they call them references. So then, for every string in the array, you have to traverse a reference to the string object. And then for every string object, you have to traverse another reference to the character arrays, for example, if you're interested in processing the characters in the string. So if you have a lot of strings, this is going to take a lot of time, first of all, to figure out where are all the bytes. And then you have to make many short copies, depending on the length of the strings, but say they're tweets or something. That's a lot of small copies that you have to make. And you pay the latency every time, and it's just not going to give you very, very good performance. In fact, I will skip over this one quickly. At the previous, there was an OpenPOWER workshop at the ISC last year, and we showed this slide already where we tried to do this as fast as possible. And we just realized that we're basically looking at these lines here because the top ones here are actually cheating, and a Java programmer would never ever try that method. But basically, you're pretty much bound by the structure of this data in memory a lot, and you can change it as a programmer. I mean, you can do some tricks maybe, but then you can process the data like you're used to anymore. So you can see the bandwidth here, and actually if the objects are very small, you're not even going to go over a gigabyte per second of bandwidth. And nowadays everybody's talking, well, today we've heard many people talk about like, okay, we're increasing the bandwidth a lot. But yeah, I mean, if your data structure is nicely contiguous in memory, you're never going to achieve that bandwidth. All right, so this doesn't only happen with Java. It happens with all kinds of tools that are written in these high-level languages that run on virtual machines and interpreters that handle all this memory management for you. And this gives a lot of what we call deserialization or serialization overhead. So it might be that you have a sort of a setup like this. You have some application running on top of Apache Spark. There's a JVM there. You might want to go and send some stuff over the network or to disk or to some Python library you're using to do some analytics. Maybe there's even a native library. And maybe there's even an accelerator there that wants to use that data. And, well, we've just seen that this thing here, it just doesn't, it's not going to give you the performance that you want. So this is something that's addressed by the Apache Arrow project. People have recognized this and they said, well, we have so many tools, so many different platforms. Why don't we sort of come up with a unified format for the data in memory, and then we build a lot of libraries on top of that through which all these different languages and interpreters can actually access the data, write the data structures in that format, and read from the data structures in that format. So basically you're kind of trading, it costs you a couple more instructions, of course, to go through those library calls for the Apache Arrow library. But you gain a lot of speed because you don't have to serialize anymore. Many of these projects, like Apache Spark, are actively integrating these, actively integrating Apache Arrow into their backends as we speak. So we thought, well, that's nice, and there's a lot of implementations going on for many different languages and frameworks. There's even a GPU a part of Apache Arrow that does it for GPUs. But there was nobody was working on FPGAs. So we thought, let's do that. We can do that because of several reasons. The main reason is the data in memory is standardized through the format specification of Arrow. So that means that if we know the type of the data, we know how big or where the data is in memory, then we can load it onto the FPGA. And what we gain is we don't have to serialize anymore if we are able to read from that format as well with an FPGA. So the same advantage for all these other libraries and interfaces goes for our framework as well. So we call the framework Fletcher, and it generates structures in the FPGA to read from the Arrow format. Now I will give you a super fast crash course on the format in memory. So the goal of the format is to store everything in buffers that are as contiguous as possible. It is possible to have some fragmentation there, but the ultimate goal is to not have any fragmentation, not be burdened by a garbage collection if you don't want to. So I have an example here with a table. Here's a table. There are some columns here. There are some rows. This is a column with some floating point numbers. This is a column with some strings, and this is a column with a structure that maybe some programmer thought would be nice to have in his program. Now Arrow defines that if you have a schema, well, sorry, let me put it like this. So if you have a table like this, there needs to be a schema that tells you what the types are. So this is basically like a type definition for the whole table. So these are the fields of the schema. So in the case of this floating point number here in the first column, you can just say like, oh, the name of this column is A, and it contains floats. And there's another thing that Arrow allows you to do, and that's to specify that data can be null or invalid or whatever. So that's why this thing is here. To simplify the other examples, I left that out in these ones. So it allows you to define lists of other types. List of, in this case, it's a character. So all the types that are fixed with, we call them primitives. But you can also make lists of lists, or lists of structs, or lists of lists, if you wanted to. So you're really flexible as a programmer to define any data type you want. And then there's also structures, which is just a grouping of other types. So you can also have a struct with lists or something if you wanted to. Just for the sake of the demonstration, I'm trying to keep it simple. There are more data types in Arrow, but we do not support them yet. So there's also dictionaries and union types. But I will just focus on these. So what Arrow will do for you is you can build up this table in memory, and then you will have them in what they call buffers. So for a fixed width thing like a float, you have a buffer that just holds the data, like we're used to in C, for example, a big array with floats. But because this thing is nullable, there's also a validity bitmap. So it says it has a bit to say if this value is actually valid or not. So that's two buffers, and they can be huge or they can be small, whatever. But in any case, if we go from one framework to the other, from one tool to the other, it stays there in memory. It's not being copied. The memory is going to be shared between the programs. And through the arrow libraries, you can access these elements without doing any serialization or copying. Furthermore, because it's so contiguous, it's easier to send it over the network, for example, which these cluster computing frameworks do a lot. So they might shuffle at some point, shuffle the data over to other nodes, and then if it's in a contiguous buffer, that's going to be faster. So then there's also the list. So they do this quite nicely. So there's going to be a big buffer that holds all the data that's in all of the lists, and then it just has a second buffer that points you to a specific offset for a specific index in the table. So for example, here where the word tasty starts, I just have to look at this index. I get an offset of 6 for this table, so it's basically somewhat like a pointer. Now this is nice because if you would just do lengths, for example, you would have to go through the whole buffer to figure out where actually the word starts in the data buffer. But because it's offsets, you could process this thing in parallel, for example. Now for the structure, you just basically have two buffers where the indexes have to correspond to whatever is in whatever belongs together in the structure. So we took this format specifications. Again, you can make crazy schemas with this if you wanted to. I'm trying to keep it simple here. So we took the format specification and we thought about the following approach to get this to FPGA. So what we do is we basically start with an arrow schema that tells us what the format of the data in memory is. Then we throw this into a thing we call our interface generation framework. This is basically what Fletcher is, our framework. You then get an HDL template or an HDL template to which you can add your own accelerator designs. So you could use HLS or manual HDL coding to get your accelerator implementation. Then you combine these together, synthesize, place, and route. And that's what you do during compile time. So during runtime, we provide, you start with the data source on disk or from the network. Through the arrow libraries, you build your arrow table in memory. And then on the FPGA side, our generated interface will be here. And the data streams are delivered to your hardware accelerated function, as we call it. In Snap, it would be called something like an action. And the strength of this is that what we allow is that this hardware accelerated function can speak about the data to the interface in terms of indices in the table. So that means you don't have to provide like a byte address or something for your data here. No, you just say from that column I want that row. And basically the streams will provide you with exactly the data type that was specified in the schema. So one thing you have with HLS, you're kind of limited to the data types that are known in C, such as characters, integers, etc. But we actually provide the actual data type here as a stream that you define in the schema. So that's quite powerful. I'm not sure how many people have ever done FPGA acceleration, but yeah, usually it takes a lot of time to figure out all the byte addresses, the alignments, reorder all the data in such a way that it becomes usable finally in the functional part of your accelerator. So this is a big advantage. Now, let's focus a little bit on this part here. Depending on what type of platform you use, this is going to look slightly different. So this part is getting the data to the generated interface. Now, if you use a classical type of accelerator setup with PCI, maybe on an Intel machine or whatever, it's going to look like this. So the FPGA is not able to access the host memory. not easily at least. So what you have to do is first you have to make a copy of your data on board. So most accelerator cards have some DDR. You just copy the table there, and then we can start reading from that. Now with CAPI, we don't have to do that because first of all, this is a streaming interface. It just streams the data there. So we don't have some sort of data locality if you don't want to. So that means that just streaming it in from right away from here through the generated interface to your hardware accelerated function is good enough for us. So we don't make that extra copy here that you would need if you didn't have CAPI, if you weren't able to access that virtual address space. That's a big advantage. Now, looking at the time, I will not go into too much detail about how we do the hardware generation. This is basically to read fixed width data. There are some units there that figure out everything, do the reordering for you, and provide you with the actual stream. There's some logic there to interface with the host memory. You just provide it with the first and the last index in the range from the table that you want to load. So there's the same for variable length data. We actually combine two of those previous blocks to turn the offsets into new commands for the other block that then requests the appropriate range of the data here and then streams it to the user. Again, seeing the time, I'm just going to skip a little bit of this. Also, the structs is just two of those together. Now, there is a lot of other hardware features. I have to thank my colleague Jeroen a lot for this. He's an amazing VHDL programmer. All kinds of stuff is parameterizable in our framework. So we wanted to validate the proper functioning of our framework. So what we did, we just generate over 10,000 random schemas that get increasingly more like a primitive as they grow. So for example, this crazy schema here, I'm not even sure if anybody would ever think of that. But we generate the test vectors and then we run in simulation the requests, and we check the stream's output if it's correct. So all of this works, so it's been quite well tested. And in the end, of course, it only works if it actually works in reality, of course. So we did a little experiment. We used two systems. One system is the Amazon system. They have a cloud-based system that they provide FPGA accelerators on them. It's called the EC2 F1. They have Vertex UltraScale Plus accelerators there. Officially, it's not known what the what the card is. I think I know, but it's a big FPGA. We have, on the other hand, the Power 8 CAPI system. The one we use had a KU3. And we basically have an experiment where we're doing regular expression matching. And we have a little design here that is the same for both systems. So the lower part is the same for both systems. We also have some abstraction layers in our framework. And there's one of those things that we generate from the schemas. We call it a column reader. And this one is going to do the bus requests on the host memory. And it provides the streams to the functional units. And these are the little purple thingies here. And they're actually the regular expression matching units. So we have many of these. So we do 16 of them in parallel. And then we also parallelize this whole thing. So they all process the same string. And then we have multiple of these in parallel as well. So this guy was able to fit 16 of those. Well, actually, we could put way more of those, but you will see it didn't matter much. This is a much smaller FPGA. We were able to fit 8 of them comfortably. I also have one with 10, but that didn't really help much. So we have twice as many of them being matched in parallel, and half of that here. So on the top part for Power 8 with CAPI, we're using the Snap framework there. So I'm not an HLS guy, so this was just normal VHDL, but still it was really easy to get all of this connected. Once you're using AXI, it worked very well. So one of the great advantages for the Snap framework, and that's also the libc, XL, and PSL thing, is that you can actually do hardware-software co-simulation. So, like Bruno was saying, I mean, if you have some sort of error in your software or in your hardware, you will be able, through the PSL simulation engine, to find that error, and you don't have to build your whole FPGA image first to figure it out. So on this system, you also have simulation, but either you do Verilog simulation, yeah, but for your software part of the whole thing, you can't really connect with the simulator. So that's a bit of a drawback here. This is a bit of a this is a customized thing that Amazon built. This is a classical setup for an FPGA accelerator. I won't go into too much detail. So the results are more interesting. So on the left we have one of those instances. This is an Intel machine. It has only 8 hardware threads available for us. So what we did is we measured how long Java took to do this job. How long Java did it with 8 threads. We have a very fast C++ implementation that we also do with 8 threads. We also do it where we store the data in the arrow format, and we also have the FPGA implementation. So on the x-axis, this is the amount of bytes of the whole data set, including including all the buffers, and this is the runtime. So we can see that yeah, the single-threaded implementations on the Intel machine are a bit better, but the multi-threaded implementations, yeah, of course, we have way more threads on the Power machine, so they're much better. Yeah, starting up the threads for low data sizes is taking some time there. Now, the FPGA part is the most interesting part, of course, for us. Well, of course, the first thing we were happy with is that it's actually faster than the software. That's always good. So on the next slide, I have a slightly more interesting picture related to what we built. And this is the runtime. It's zoomed in for a data set of 1 gigabyte of strings, slightly over 1 gigabyte of strings. So yeah, I mean, this took so long. I didn't want to make it a logarithmic plot here. But yeah, we can see that Java just takes a lot of time. Even if you spawn more threads, it's going to be much better, but it's still taking a lot of time. And the FPGA just takes way less time. Regular expression matching is a quite well-known example of an application that works well on FPGA. That's why we picked it. So now the interesting thing to look here is I also plot the time for serializing that data set. That's the thing we were trying to solve, right? So how much time does it take to serialize that data set before I could send it to the FPGA? Now, in Java, it took us 3.14 seconds to serialize that data. C++, it took us 1.99 for the Amazon system. On the Power system, it's slightly more, 5.34 and 3.6 for Java and C++ respectively. Now, if the FPGA just takes, well, half or a third of a second to process that data, but your serialization is this much, actually in this case, it will even take more time to serialize and process the data on FPGA than to just do it on C++ with all the threads enabled on the Power system. So even if you have this tremendous throughput in the hardware, the software stack also has to kind of, you know, correspond to that a little bit. And using all these very high-level things, yeah, it's not going to be good enough. So I think, you know, combining Apache Arrow with our framework has been a quite nice experience so far. It's doing exactly what we hoped it would do. It is just going to get rid of the serialization overhead for us. That is usually going to kill the performance in many cases that we can do. Now here you have the throughput on both machines. One nice thing that we saw is even though we have less functional units, I mean actually in both cases it's bounded by the bandwidth. This is on CAPI 1.0 still. I'm hoping to do this on CAPI 2.0 soon. Yeah, I mean the bandwidth is just much better, and it's also much easier to do it on with CAPI and Snap because we don't actually have to copy the data to the local DDR memory first. So we get about 3 gigabytes per second total application throughput. So we were we're kind of close to that peak bandwidth that we saw in one of the previous slides of 3.8 or something of read bandwidth from CAPI 1.0. So that also shows that our framework itself is quite efficient already. Yeah, so Amazon says that their system can go up to 1.5 gigabytes per second. We did some tricks to make it go faster. I still have to tell them what to do, how I did that, I think. Yeah, this has to go through the OS, so it's much slower than what we are used to from CAPI. We don't have to go through the OS. We just give it a pointer of the buffer, and it starts going. All right, to conclude my, my talk, serialization may cause significant bottlenecks in big data frameworks. We've seen that from previous measurements too. It's going to prevent the effective deployment of accelerators in some cases, especially in these guys that work on very high-level language frameworks. Well, Apache Arrow has been designed to alleviate these bottlenecks, and we have shown that you can also do that for FPGAs, and actually you can generate a nice interface on the FPGA that will increase the programmability for that one as well. Now, we made it work on Snap. On our repository is open sourced. Actually, there's a little tutorial how you can run it on Snap. So if there's any questions, I would be happy to address those. That's right. Yes. Okay. Yeah. Let me go there. So this is what you would normally do, right? Because all the data is in this JVM here, and you have to serialize it before you can send it to the accelerator. Exactly because of this problem. The data structure is not the one you want in your FPGA. Right? So we looked at the Arrow format, and we said, wow, that's a pretty nice format that can actually also work on FPGA. Now, this is how Arrow works. There's some sort of layer that will make sure that the data in memory is formatted according to that specification. Okay, so yeah, exactly. Yeah. Any other questions? There's a question there.
Slide 7. I think you have some acceleration. I guess some acceleration. Just help me understand your scale.
Okay.
Speed up. What does the speed up of 0 do?
Yeah.
The same?
So this is the speed up compared to one thread for for the various types of things that we try to serialize as fast as possible from the JVM.
So speed up of 0.3 means 3 times slower.
That
30% faster.
No, that is 0.3. One is 100. One is the speed up of 1. So 0.3 is a slowdown of. Yeah, that's 30% of the original. Yeah, so yeah, you're looking at this, of course. So it gets slower as you spawn more threads, and this is because there's a lot of resource contention and multiple threads trying to access the same objects in Java. At some point, it's just gonna, you have these locks and monitors and everything that are just gonna slow it down. This is what we experienced here. I'm more of a hardware guy, and probably Java people will tell me, okay, you can do it in this very exotic way. I'm not saying that this is like the best ever, but this is what we see. So, yeah, a couple of threads will do fine until it just collapses there for this implementation at least. Yeah, this is the JNI thing. Yeah, that's a classical way of getting your data out of Java into C land. But it's a good question. Yeah. We have a paper on this published in the workshop at ISC 2017, so you can read the details. Any other questions? All right, so thank you for your attention.